I think one of the reasons why the CCDA certification is so cherished by so many individuals out there is because it really gives us a chance to explore a wide variety of really hot technologies. We've talked about data center technologies in here in depth. We've talked about security technologies in here in depth. And now we're going to talk about voice and video, yet another area that is exploding in popularity in modern networks today. So, in this CBT Nugget, let's get started talking about designing for both voice and video over IP infrastructures. Okay, I couldn't resist the absolute cheesiest clip art that I could find to convey voice technologies. Yeah, gotta love it. All right, what are we gonna do in this CBT Nugget? We're gonna do two things. It's going to obviously take us a little bit of time and it's hugely important, but it is centered around two things. We're going to review the fundamentals of voice and video technologies. Absolutely. We're going to review this because it's critical to review this information to make sure we have a good, strong foundation to start talking about the detailed and very particular requirements that we're going to have to fulfill when we design a voice or video solution for a converged network. And this word is so important, converged network. What is a converged network? Don't forget, when we have our devices, right, that are going to be moving our traffic now, they're not just moving data. Yeah, for the longest time, it was just data that we were interested in transporting. Now we're putting right next to it traffic like voice, and right next to that, traffic like video. So all of these particular traffic forms need to coexist, or what we call converge together on the network. Don't confuse this with like something like routing protocol convergence. Here, when we say the converged network, we're talking about voice joining data, joining video, and all being sent down the same pipe. Now, first things first, we have voice, right? Traditional voice traffic, a traditional telephone network. And when we speak into that phone, it creates this analog waveform. To get this information over the data network, we need to convert it to digital. There are several steps in this conversion process. One of them is to go ahead and filter. Take this signal and filter out the speech that we care about. It turns out that when we speak, most of that energy ends up ranging between 300 hertz to 3400 hertz. So, very early on, digital telephony researchers figured out that there was about a 3100 hertz bandwidth for standard speech. So they created a coder decoder. Yeah, a codec that would enable the conversion of this analog waveform into a digital frequency. Then what has to happen is sampling of this voice traffic. So they figured out something called pulse amplitude modulation as a way to sample this filtered audio. They would sample at a rate twice the highest frequency of 4,000 hertz. This would be equal to 8,000 times per second, or sampling every 125 milliseconds was what they developed. And then finally, this information has to be digitized. This is done with pulse code modulation. Sure, taking the analog to digital converter on the source side and making it happen. And then on the other side of the connection, we need to go from digital to analog to play back to the person on the other end. So, fundamental to the process of taking voice and putting it on the data network, we need to do the conversion, and this would involve filtering, sampling, and digitizing technologies. Now, once you figure out how to take the analog speech and convert it to digital, and then vice versa on the other end, you're well on your way to supporting voice in the data network. But hold on. We're going to need a set of standards that describe session setup, monitoring, termination of calls, and we're going to need this to be standards based so that the equipment from a whole bunch of different vendors can interoperate. And that's what H323 or H.323 is all about. As a matter of fact, it's actually a set of standards. For instance, a substandard within it is H.225, and this defines and spells out call signaling that we should have in a voice over IP network. There's H.245, and this spells out capability negotiation and media stream management facilities. So, lots of different standards within this H.323 umbrella so that we can have the equipment from many different vendors interoperate in a voice over IP world. Now, the H.323 standard defined many components that would be used in a voice over IP world. One of those components is what's called a terminal. What is a terminal? Well, how about a voice over IP phone? Sure. Or how about a PC running software to do voice over IP, right? Sure, we call this a soft phone when we have phone technology running right on the personal computer. So, the first ingredient, very important, a terminal, something that the individual can actually use to make a voice over IP call with. Another component they identified is a gateway. A gateway does all kinds of conversions for us, right? Maybe we're running a bunch of equipment that is doing the H323 standards, and then right at the edge we put a gateway so that we can communicate with non-H.323 components out there. So gateways are all about conversion for us from one signaling type to another, from one set of standards to another. We call this a gateway. Now, these standards makers also identified a gatekeeper component. What the gatekeeper does is it routes calls inside the domain. In fact, the domain is called the zone in gatekeeper terminology. So a call comes in, a gatekeeper would say, okay, I know where to send that call. Something else that the gatekeeper would do would enforce quality of service requirements for the particular call. So yet another component, the gatekeeper. And finally, this standard identified a component called a multi-point control unit. And a multi-point control unit would allow for things like conferences, where you might have multimedia to play, like hold music while you're waiting for the conference to begin, and then once all the people join for the conference, you need to mix all of their audio streams in the conference. So a multi-point control unit was identified to make things like conferencing a reality. What about video? Well, a huge standard that you should be aware of when it comes to video is H.264. H.264 really did wonders from the standpoint of compression. Yeah, you probably know that video is huge. How do you know this? Well, you've taken some personal device and you've taken this great video of your kitten playing with a ball of yarn, and then you've wanted to share that with the world, because after all, everybody should see that. So you take this video and you put it on your personal computer and you go to email it. And your email program says, whoa, nice try. Your video of your kitten playing with yarn is 8 gigabytes in size. And I can't mail that. So we realize that there needs to be really good compression if we are going to be sending video over the data network. You know, the H.264 standard when it's compared to other algorithms, it can actually produce better quality video, and it does so at about 30% less the file size. So, when we are dealing with video that we want to send of a pretty darn high quality, but we want to be careful about file sizes, H.264 is a standard that is worth consideration. Now, let's talk about a typical Cisco voice over IP network, right? There may be other vendors that do other stuff, but let's go ahead and just focus on what a Cisco voice over IP network might look like. If you see a router and that router's got a big V on it, it's what we call a PSTN gateway from Cisco. It's a voice capable router. So it'll make a traditional connection to an IP wide area network, and it can also make a connection to the public switched telephone network. Sure enough, Cisco will call this in kind of standards terminology that we've already discussed. It will call it a gateway. Notice it can take voice in from the traditional voice environment. It can take this voice and digitize it and send it over the IP WAN. Now, something that gets tucked on these routers is called DSPs, digital signal processors, special circuitry that's put in this device so that it can do all this voice stuff at a nice high rate of speed. Now, that device might connect into, of course, a catalyst switch. I'll just say SW for switch here. And that switch might plug into a voice over IP phone. And how does that voice over IP phone get its power? Well, it doesn't have to plug into the wall. It can get its power from power over Ethernet. Yeah, this is a cool feature that many Cisco switches can do. They can provide the little bit of power that a phone needs to, light up its display and actually ring when someone calls it. That little bit of power that's needed, that can come from the switch. Cisco invented their own power over Ethernet method, and then they went and supported the open standard that exists for power over Ethernet. Now, you need some brains of this whole operation. You need a device, right? You need a device that can handle all of the call routing and the call setup. This used to be done by what was called a PBX. But the PBX replacement in a voice over IP world is, drum roll please. I need a drum roll sound effect. Here, let me try. All right, that was awful. The replacement for the PBX in our environment here is called the Unified Communications Manager. Yep, it used to be called Call Manager, and a lot of people still call it that. But Cisco said, we need to give it a much fancier name. So it's the Cisco Unified Communications Manager, otherwise known as CUCM. And this is the brains of the operation, and it is a PBX replacement. This is such an important device that, as you might guess, it comes in a wide variety of form factors. It's software you could install on a Windows machine. It's software you could install on a Unix machine. It's an appliance that you could mount in a rack of your equipment. So lots of different forms. There's even an Express version. And as you might guess, the CUCM Express is a real simplified version for very small environments. There'll also be in your network a voicemail component, right? Sure, Cisco has products that will help you with voicemail in this voice over IP environment. In fact, what's really neat about voicemail in a voice over IP world is that you can take it and send it as emails, and you can do all kinds of fancy things with it in order to simplify the way in which individuals will get their messages. So, here we have it. A typical Cisco voice over IP network. So at this point in this nugget, you're all excited. You're like, okay, I'm ready. I'm ready to go. I'm ready to design for my client this voice over IP infrastructure. And my client is going to be able to save on public switch telephone network toll charges. Yeah, they're going to be able to make free calls. Everybody loves free calls. My client's going to be able to fire all of their staff that does the traditional public switch telephone network stuff. We can get rid of the PBX. We can sell it on eBay. We can fire all those people that we had doing all that PBX stuff. Oh, we're going to save all kinds of money. But listen, it's never that simple, is it? In fact, I need to paint something here for you that is going to be something that we really need to consider heavily in the second half of this nugget. And that is the fact that data, voice, and video, sure, they're all really different. Take data, for instance. When it comes to delay and variation in delay, variation in delay is called jitter. Okay? See, delay is one thing on your network. Delay is often pretty predictable, right? And that's fine. If your web client and your web server know that there's going to be about a 500 millisecond delay between them and it stays consistent, you can design the browser and you can design the web server to accommodate that. But what if the delay isn't consistent? What if 1 minute the delay is 500 milliseconds and the next minute the delay is 3,000 milliseconds? This is called jitter, variations in delay. Now here's the thing. Data, when it comes to delay and even variations in delay, it's pretty tolerant. It could really care less. I mean, think again about a web browser. Even if there's huge variations in delay, the web browser does a pretty good job of saying, no big deal, I don't care. And what about packet loss? Well, data is pretty forgiving there. You can have up to 2% of your packets lost, and when you're surfing the web, you wouldn't really even know it. Yeah, you really wouldn't even know it. Now, what about voice? Well, you probably have already gotten my punchline here. Voice is intolerant. Yeah. It's lactose or it's jitter intolerant. Yeah, it's jitter intolerant. It really is plagued by jitter. If the delay isn't predictable, if it's not consistent in your network, this could dramatically affect voice quality. Yeah, I mean, literally like, are you there? Hello? Hello? Are you there? Those type problems. And as you might guess, we want to go for less than 1% packet loss in a voice over IP network. Video? Well, video is also intolerant of variations in delay. And guess what? It is going to be even more upset by packet loss. We try and do less than 0.05% of packets being lost in a video environment. Otherwise, we're going to have choppy, problematic video. So you notice that the data, the voice, the video traffic, by no means are they created equal. They're going to be attempting to share the same overall pipe in your network infrastructure, and they have pretty dramatic different characteristics here. I'll even add something else to this particular equation that's interesting. Data, for example, tends to be bursty in nature, right? Sometimes there's a lot of it. Sometimes there's a little bit of it. Sometimes there's a little bit. Sometimes a lot. Sometimes a little. Yeah, when you look at a data pattern, I'll draw it down here in the bottom, you see like, whoa, 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 that's what the pattern looks like. You know, someone's downloading a big file. Nope, now they're not. They're just web surfing. Now they're just doing Telnet. You have these variations. You have this bursty nature of the traffic flow. Guess what? With voice traffic, in particular, not so much video, but with voice traffic in particular, we have what we call a benign traffic flow, a smooth traffic flow. It's very predictable. We digitize the voice packets, we chop them up into tiny little packets, and we send them, and it is very predictable and benign how much bandwidth that particular resource is going to use. So, these traffic forms are indeed very different, and this is going to lead to tremendous challenges that you need to be ready to take on as your network's designer. Now, when you see just how different voice traffic is and just what different requirements that it has, as we just did, you're not surprised that there is going to be a wide variety of call control protocols that are going to be needed to make voice communications work over our data network. And then in addition to that, we're going to need a transport protocol to carry the voice conversations. Let's cover that first because it's real simple. It's RTP. Yeah, RTP is the protocol that's going to carry our tiny little voice packets. This is the real-time transport protocol. You see, what we're going to do is we're going to take the little voice packets and we are going to send them utilizing the user datagram protocol. We're going to send them as UDP traffic. This doesn't give us any reliability whatsoever. You know, UDP is all about efficiency, not reliability. We learned this back at the CCNA level when we were talking about TCP at the transport layer, transmission control protocol, versus the unreliable connectionless UDP at the transport layer. So real-time transport protocol, RTP, is going to encapsulate the voice, which is encapsulated in UDP packets. So that's going to be the protocol we use for transport. You're probably not surprised to learn that we have the RTP control protocol. Yeah, so this is RTCP. Yeah, so we have RTCP, the RTP control protocol. And this RTP control protocol is going to be used to do things like, have the actual RTP exchange be monitored, and particularly monitor the RTP exchange for quality issues like maybe packet loss or maybe too high of delay or variation in delay that we call jitter. Some other control protocols we might run into, how about Q.931? This is for call setup. We have H.245. This is for call capabilities. And we also have what's called RAS signaling, another call control protocol. RAS signaling is for registration, admission, and status. So things like bandwidth changes or registration issues can be handled by RAS signaling. So, one transport protocol to help out with the movement of voice traffic, that's RTP, and a whole host of call control protocols that we need for a successful voice over IP implementation. Okay, so this is really starting to make sense to us. How do two voice over IP phones, how do they communicate? They communicate by taking the little voice packets and encapsulating them in UDP, and then this gets encapsulated by RTP. So we could say that they use the real-time transport protocol, RTP, in order to communicate. But wait a minute here. We remember that the PBX replacement in a Cisco voice over IP world is the Cisco Unified Communications Manager. How does the Cisco Unified Communications Manager talk to these IP phones from a management perspective? Well, that is the skinny client control protocol. That's right, the SCCP. This is a Cisco invention that is used for the messaging that's going to be required between IP phones and the Cisco Unified Communications Manager. Now, wait a minute. The Skinny Client Control Protocol is a Cisco invention. What if we have phone systems that don't know about it, but we still want to control those with the Cisco Unified Communications Manager? Well, that's where SIP comes in. SIP is the Session Initiation Protocol, and SIP is not Cisco proprietary. So we have our Cisco Unified Communications Manager. We might have a bunch of equipment that is using SIP. We can even have what's called a SIP proxy server, and that device can go ahead and make a connection to the Cisco Unified Communications Manager. Because thankfully, CUCM also supports SIP in addition to the Skinny Client Control Protocol. So SIP is another peer-to-peer protocol that's an open standard that we can find in our voice over IP networks, and the great news is Cisco supports this in CUCM. Now, if you're impressed with what the CUCM can do, you're about to be even more impressed. You see, Cisco invented a technology called the Media Gateway Control Protocol. While they originally invented it, it soon became an open standard. So MGCP is now an open standard. What we have is we have the CUCM that can speak MGCP, and here's what happens. Let's say we have this Media Gateway Control Protocol speaking router, R1, and then we have another MGCP speaking router, R2. These devices have phones, voice over IP phones, that connect to them that can speak the Media Gateway Control Protocol language of love as well. So sure enough, all these devices are connected together. What happens is this device goes to place a phone call, and MGCP is used to communicate that information to the CUCM. The MGCP protocol then goes ahead and establishes this phone ringing. And once the connection is created between these two phones, then MGCP can step out of the equation, and these two phones will communicate directly with each other using the real-time transport protocol. So, in an MGCP network, we have what's called a call agent. And that's the role here played by CUCM. And this call agent is responsible for controlling these MGCP gateway devices, in our case, these routers that don't have any forwarding intelligence inside them. Instead, they rely on the call agent. So now that we've taken that lengthy journey through the world of the fundamentals of voice over IP and the particular protocols and devices that we'll run into, let's talk about the challenge of designing the requirements for a properly implemented voice over IP network. One of the things that we absolutely have to consider, as we indicated, is delays. We know variation in delay is a nightmare, and we'll talk about that soon here. But what about just delay itself? Well, the ITU says, look, if you can get the end-to-end one way, okay, it's important to realize that this is just one-way delay measurements. If you can keep it between 0 and 150 milliseconds, the one-way delay from one phone to the next, you're going to be in really good shape. They also recognize that 151 milliseconds to 400 milliseconds is probably going to be acceptable in most environments. And then, of course, they identify anything greater than 401 milliseconds, we are most likely going to run into some serious problems when it comes to voice over IP call quality. Now, When it comes to solving delay issues, one of the first things you want to do when you're designing is mentally separate fixed delays from variable delays. Sure, for instance, there's something that we call propagation delay, right? This is how long it takes to get from point A in the network to point B in the network. I mean, after all, there is going to be some delay as the data signal travels from point A to point B. Maybe it's, 6 milliseconds per kilometer. I mean, it's going to be measurable in your network, and notice there's absolutely nothing you can do about this particular fixed delay component. It is what it is, as a wise man once said. Then there's a component called serialization delay. This is the time that it takes to take the frames and put them onto the particular link. There's not really much you could do here. I guess you could make the packets as small as possible, and that's what we do in voice. And you could also make faster links. The faster the link, the faster the packets can be put on that link and sent on their way. And then there's processing delay. And what we mean here is, of course, the codecs, right? The conversion of the analog signal into the digital signal, or vice versa, the digital signal's conversion back into the analog. Cisco tries to help us here with those digital signal processors, those special components on the voice speaking equipment that will help speed things up from a processing delay perspective. So, fixed delay components, yeah, 3 of them come to mind: propagation delays, serialization delays, and processing delays. And it's a variety of things we can do about this when we design, from absolutely nothing to installing special circuitry to speed things up. Now, fixed delays don't tend to scare us as much as variable delay components. And that is one big one I want you to know, and it's queuing delays. Sure. By the way, there are many different spellings of queuing in this sense. You'll see it Q-U-E-I-N-G. You'll also see it Q-U-E-U-I-N-G. Lots of different spellings in the literature. However you spell it, doesn't matter how you spell it, it means that when an interface gets congested, when an interface starts filling and a little voice packet shows up, we are going to have variations in the amount of delay that we are going to experience in your voice over IP network. I'm going to teach you a whole bunch of solutions for this variable component of queuing delay in this particular CBT nugget, but suffice it to say, we got a real potential problem on our hands here. One of the solutions that was implemented to try and help with this is something called de-jitter buffers. Yeah, the idea was, why not make this unpredictable variable delay, which is such a problem, why not try and make it more predictable? In other words, if we see that there's like a 40 millisecond variance in delays, why not just delay things in a buffer by that amount, and now we take the unpredictable nature of the delay and we make it predictable once again? Well, this is certainly one approach, and this can be quite successful. The de-jitter buffer approach, the great example of this that I have for you is when you do live audio streams over the internet. One of the things that I've done before is I've listened to my beloved Boston Red Sox in Major League Baseball over the internet. Now, one of the problems when I do this is I can't answer the telephone. Why can't I answer the telephone when I'm listening to an internet audio broadcast of my Red Sox? Because I'll be about 30 seconds to even a full minute behind the actual live action. What have they done? They are using dejitter buffers to take care of all of the call quality issues that I would get over the public internet so that I can hear it with decent quality. They're buffering it dramatically and they're playing me the signal out of the buffer. By the way, there's also a large amount of propagation delay, right? We know that's a fixed delay component, but that's going to be in there too. So, very, very interesting, this concept of working with delay. And as I promised you in this particular nugget, we'll go ahead and we'll solve a lot of these issues or show you the solutions you can design to solve them. By the way, I never did answer the question, why can't I answer the phone? Yeah, my brothers would be calling me from Boston to celebrate something that happened in the Major League game. So I'm behind the live action. I couldn't go near my phone because they might spoil the drama for me. You know what another problem can be in our voice over IP infrastructure? Echo. Yeah, echo. This is when the caller hears their own words repeated to them. Echo turns out to be a function of two things: delay, which we've been worried about all along here, and what's called magnitude. Yep, so delay and magnitude are the sources of echo. So this becomes a problem as the delay gets bigger and the magnitude or loudness of the overall call gets louder. What is done to solve this problem is literally components that do echo cancellation. These are called echo cancelers. What's interesting about echo cancellation is while we need it in our voice over IP equipment, and Cisco does a great job of building it in, it doesn't want to eliminate all echo. Yeah, that's what's fascinating about echo. The caller wants to hear their own voice. It's comforting. It actually proves to them that the call is working. The issue is there can't be a big delay on when they hear their own voice. The rule of thumb is if it's anything greater than 25 milliseconds when they hear their own voice, it's going to be, causing a pretty bad nightmare. It's going to be so distracting for them that they're not going to want to continue with the call. Now remember earlier we talked about those codecs that we're going to need? The codec is going to help us when it comes to converting analog to digital and then digital back to analog. Well, your choice of codec for your customer, is going to be hugely important. Let me give you two great examples. There is a codec that we can use, a standard codec that we can use called G.711. G.711 is awesome quality. I mean, we give this 5 stars. In fact, there's actually a rating score for quality, and it's called the MOS, or Mean Opinion Score. And it's a rating of how good the call quality is. And sure enough, the call quality rating for G.711 is awesome. But it's going to require 64 kilobits per second. Yeah, it's going to be 64 kilobits per second of bandwidth that's going to be required for that particular call. Now, you might look at that and say, well, in our environment, no problem. Well, no problem certainly for the local area network. And that's where we tend to see G.711 implemented, in the LAN where bandwidth is plentiful. But what if we're in a WAN environment and we've got to send a lot of calls over the wide area network? And like I said, in this particular environment, bandwidth might be precious. Well, we could turn to something like G.729. G.729, no, it's not going to have the quality that our G.711 did, maybe 3 stars, right? But G.729 is going to offer about 8 kilobits per second. Wow. So, notice the choice of codec is going to be hugely important. impacting call quality, but most importantly, perhaps, impacting the bandwidth required for these voice over IP calls. Now, when you're provisioning the amount of bandwidth your customer is going to need for their voice over IP implementation, you can't just say, all right, we'll do G.711 and we'll go ahead and know that it's going to be like 64K per call. No, careful. It's not going to be that simple, and you want to be precise, right, when it comes to provisioning bandwidth. So for that, do a search on the internet for voice calculator, voice over IP calculator. Cisco's voice codec bandwidth calculator link will come up. Now, just keep in mind you do need to be registered at cisco.com to access this tool. That's a free registration, of course. So just register up at cisco.com and you'll be able to use this tool. So here we're saying, all right, I'm going to use G.711 and we're going to be doing voice over IP. And the worst case scenario in this particular segment of the network, worst case is we could have, let's say, 10 calls simultaneously. So we give this information. Now it says, okay, what's your voice payload size in bytes? Okay, 160, that's fine. That's our voice payload size that we're going to use. And guess what we're going to do, potentially? We're going to squash the RTP headers. Yeah, you could potentially do this. If you were really worried about bandwidth and wanted to save on bandwidth, you can take those RTP headers. Remember, we had the voice payload right here. We had the UDP header information, and then we have the RTP header information. Well, you can squash or compress that down to try and reduce the overhead. That's what's so funny when you look at a voice packet. The voice packet itself is tiny, and then you've got a bunch of headers. How about the IP header as well? You've got all these headers on top of it. Yeah, a voice packet looks really funny. It's small and concise, but then it's got all these headers that you can potentially squash. All right, we're in a high-speed LAN. I don't need to worry about RTP header compression. The media that we're going to be using is Ethernet, and we're not going to be doing any tunneling or security overhead. So notice the voice over IP calculator is so cool because it would allow you to take all those things into consideration. It gives you a nice breakdown of exactly what's going on as far as the bandwidth you're going to need. And sure enough, we discover in our environment the bandwidth that we need to have for voice. Total bandwidth for all those calls, including overhead, would be 915.6 kilobits per second. The voice over IP calculator is something that you want to have right in your back pocket as a tool. And again, it's a free tool. You just need to register at cisco.com in order to use it. Now, what about video bandwidth requirements? Well, as you know, they're going to be higher. And if we were using that cool H.264 protocol that we spoke of earlier, and let's say we had a Cisco telepresence system. This is a System 3000 that's out there. So you're able to speak and they can see your video at the same time. And you were to do, let's say, 1080p quality, the typical load that you're going to experience would be about 12.3 megabits per second. So we can see that this is going to be, much more dramatic bandwidth consumption. This would change, of course, rather dramatically if you were doing like YouTube, even high def YouTube. We're going to squash that down to 720p, by the way, and we'd find about 2 megabits per second required for that video information to converge over your data network. So, much higher bandwidth amounts, but the point I guess I want to make most here is the fact that these are still going to be very predictable for you to utilize when you're designing the network infrastructure. So what do we design in voice over IP and video environments to make sure it all works great? We design a quality of service solution. We talked about this back in our remote access nugget here in the CCDA series. We absolutely have to revisit it here, and I want to tell you about some specific technologies that I did not elaborate on back in that earlier nugget. With QoS, we know there's three overall approaches, right? The first, do nothing special. Yeah, do nothing special. What this really means is you're going to over provision things. The queuing mechanism that would be used would be the first traffic that shows up is the first traffic that goes out. If you have over provisioned your network, then this shouldn't be a problem. I mean, you have a plethora of bandwidth. As packets are arriving, they're going right onto the link with very little serialization delay. They're being sent at amazing speeds. Voice quality is not an issue because there's just such a dramatic over provisioning of bandwidth. Obviously, due to cost considerations, this is not all that practical. We don't see this as a solution much. Something that we can do instead, and this was what was done early on, was an integrated services approach to QoS. This involves the Resource Reservation Protocol, RSVP. And with RSVP, the voice over IP phone literally signals the various devices in the path and says, look, I'm about to make a call. Please reserve the appropriate resources for my call to ensure quality. This is often referred to as hard QoS. Something else that's done under the integrated services approach is what's called CAC, Call Admission Control. Here, a border device will literally deny or permit that device to make its particular call based on whether or not there are adequate resources to ensure call quality. How interesting. Now, this integrated services approach has its problems. It adds overhead to the whole process, it adds complexity, and it is not very scalable because you have to make sure that all of your equipment is properly configured for integrated services in order for it to work. The differentiated services approach, therefore, to quality of service in voice environments has gained dramatic popularity. And what we do in a differentiated services approach is we first classify and mark traffic as voice. This is done with a marking called EF, expedited forwarding, and the voice over IP phone does that automatically. Great. So voice traffic is automatically classified and marked as voice traffic. Then what happens is we configure congestion avoidance. Yeah, we're trying to avoid an interface from filling up. How do you do this? Well, what you do is you use something called weighted red. Yeah, when the interface starts to fill up, it's getting full, you start randomly throwing away unimportant packets. Yeah, hopefully this will allow voice packets to still be able to get in the queue. How funny. So we are sacrificing randomly unimportant packets for voice to get in. Pretty amazing. Then there's congestion management. Congestion management is the area of QoS that we call queuing. Yeah, queuing is done at congestion management. It's what to do with the interface when there is actually congestion. And the solution I want you to know for voice traffic is called low latency queuing. Yeah, low latency queuing. What you do is you put the voice traffic, the expedited forwarding marked voice traffic, in the low latency queue, and it gets ultimate strict priority at the interface. It gets sent right to the front of the line ahead of all other forms of traffic thanks to low latency queuing. Yep, it's just an absolute guarantee of priority for your voice traffic. Another area of differentiated services is traffic conditioning. Yep, traffic conditioning. What traffic conditioning refers to is policing and shaping traffic. When I just told you about low latency queuing, you were probably pretty excited that voice traffic can get the ultimate priority and that it can be absolutely sent to the front of the line. But you might have gotten a little nervous because couldn't that just absolutely cause voice to dominate the interface and potentially starve other things out? Well, no, it can't, because how low latency queuing works is that there's a built-in policer. Yeah, you use the voice codec bandwidth calculator that I showed you, and you figure out, let's say, that you need 2 megabits per second for voice. And then what you do is you reserve just that amount in the low latency queuing, the exact amount you need. And what the low latency queuer will do, it'll built-in police to that amount. So your voice traffic, if it were to malfunction and all of a sudden your voice packets were like quadrupled for some error reason in your network, erroneous reason, no problem. No problem. The low latency queuing system won't allow it to go over the 2 megabits per second due to a built-in policer. The final category of differentiated services tools is called link efficiency tools. This is where we do compression, and this is where we can do another technique that is called link fragmentation and interleaving. Let me show you about that. Let's pretend that we have this interface. And one of the things I want you to know about a Cisco interface is that it is actually divided in two. Yeah, there is what's called the HQ or hardware queue, and then there is the SQ or software queue of an interface. The hardware queue you cannot manipulate. It is first in, first out, period. End of story. The software queue that sits behind the hardware queue, it can be manipulated. This is where you would do your low latency queuing for voice traffic. So here's the story. We have this interface and, there's been some traffic that has arrived. And the traffic is, here, and it's filling up the hardware queue that's first in, first out. It's starting to spill over a little bit into the software queue, but no big deal. Okay, no big deal at all. And then what happens is a jumbogram arrives. A really big packet. Okay, here it is. It arrives, a really big packet. We call really big packets jumbograms. And the low latency queuing system says, geez, big packet, you're unimportant, but there's plenty of room in the queue, so go ahead. So, brrr, sound effect time as this big jumbogram starts moving through the software queue to the hardware queue. And that's all taking place. And uh-oh, you know what's going to happen. One of our tiny little voice packets shows up. And there's nothing the scheduler can do but stick it behind the jumbogram. Yikes. Low latency, link fragmentation and interleaving solves this problem. How does it solve it? It takes big jumbograms and it fragments them. It chops them up so that if a voice packet were to arrive, it can be snuck in between the fragments. What a cool idea. So link fragmentation and interleaving is yet another differentiated services QoS approach, and this falls in our link efficiency category. By the way, the only time you see LFI done anymore would be on really slow WAN links. Yeah, this would only need to be done on really slow WAN links where we have this problem with jumbograms causing an issue. Now, what I'd like to wrap up this CBT nugget with is just a review. Might be brand new to some of you. For some of you, it will be review. It depends on how long you've been around the telephony industry. But I just want you to be familiar with some traffic engineering terms that you might hear when you're speaking, especially to the old timers that have been around voice technologies for a real long time. You might hear them say GOS, or grade of service. The grade of service value is actually a probability value that a voice gateway will block calls while attempting to allocate circuits during really busy times. So again, grade of service is a probability of having a call blocked due to busyness of a phone system. You might hear about an Erlang. An Erlang equals 1 complete hour of a telephone conversation. Yeah. So 1 complete hour of a telephone conversation is 1 Erlang. And I know that when my daughter's on the phone, we can really ring up some Erlangs. You might hear Centrum Call Seconds, or CCS. A Centrum call second is 1/36th of an Erlang. Okay, so this is just another measurement of call quantity. And it is, as I said, 1/36th of an Erlang. You might hear the term busy hour. Not Bush, but busy hour. Busy hour is a 60-minute period in a given 24-hour period during which the maximum total traffic load occurs. Oftentimes, you'll hear this referred to as simply as the peak hour. Another particular metric that we have with traffic engineering is BHT. What is BHT? BHT is busy hour traffic. This represents the number of hours of traffic that is transported across a particular voice trunk in its busiest hour. And guess what? You report this in Erlangs. Sure, in 1 hour of true phone conversation. Then we have blocking probability. The blocking probability value describes the calls that are not completed because insufficient call resources are available. And finally, CDRs, call detail records. These are critical when we are monitoring a phone system because they record information about system usage, like who called, who did they call, what was the amount that was billed for the call, what was the total usage, what was the free time. I mean, call detail records are monitoring all of the transactions that occur for us in a particular voice system. So in this very large, very important CBT nugget, we took a look at the very complex world of designing voice and video network infrastructures. We reviewed a bunch of the fundamentals that are so critical with voice and video over IP network infrastructures, and we also talked about the vast, complex requirements that we need to fulfill when we are designing voice and video. Well, I hope this has been informative for you, and I'd like to thank you for viewing.